Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss Muller's method. So in this topic, we will introduce the idea of using interpolating quadratic polynomials to approximate the root of a real valued function of a real variable. We will look at techniques for minimizing the error as a result of using interpolating quadratic polynomials, including shifting the problem to the origin and using the appropriate quadratic formula. We'll also discuss some of the issues with such an implementation, as well as the rate of convergence. Now, the secant method interpolates 2 points to find an approximation of the root. How about interpolating 3 points and finding the interpolating quadratic that passes through those 3 roots? In this case, you'd find the root of that interpolating quadratic, and this would be our next approximation of the root. So the first step we'll take is we will rearrange the last 3 approximations of the root so that the value of the functions at these 3 points is in order. And we will choose whichever one of these is such that f at x sub k ends up being less than the least most recent approximation of the root. Consequently, in this case, we actually do want the points to be in order on the real line. If this is not the case, such as in the example below where we've rearranged the points, then we may want to revert to using the secant method as opposed to finding an interpolating quadratic. Now recall, however, that if we did have a quadratic of the form ax squared plus bx plus c, and we wanted to find a root of this quadratic, there were 2 formulas we found. And we found that neither formula was ideal. Instead, the first expression here is very good at finding the larger root in absolute value. The second expression, the one that you probably did not see until this course, is actually better at finding the smaller root in absolute value. Now, we could just find the interpolating quadratic between these points, but this leads to a rather unwieldy formula. And there's now another additional question. Which root do we pick? We found the 2 roots of the following interpolating quadratic. Do we pick the larger or the smaller? For example, on the left-hand side, we definitely want to find the larger root. But that larger root may be the largest in absolute value, but it also may be the smallest in absolute value, depending on where the second root is. On the right-hand side, it's quite clear we do want the smaller root in absolute value. But once again, now we are playing a game where we need to try to estimate which of the 2 roots we wish, and then which formula should we be using, or should we calculate both? Instead, we're going to use a strategy. We're going to shift all of the x values to the origin by x sub k. So we're going to subtract x sub k from each of the 3 x values, and we will still maintain the 3 values of the function, but now it's rather clear we want the smaller of the 2 roots in absolute value. Now, in some sense here, we now get a slightly simpler formula. Note that the denominators are the same for the coefficient of x squared and the coefficient of x, and c is just the value of the function at x sub k, the most recent approximation of the root. We also know now that we want to find the smallest of the two roots in absolute value. Consequently, we should use this formula, and specifically we should choose the sign in the denominator so as to make the denominator as large as possible. If b is positive, then we add to that the square root of b squared minus 4ac. Whereas if b is negative, we should subtract from b the square root of b squared minus 4ac. Now, as for the rate of convergence of this method, if h is the error, then the rate of convergence is h to the mu, where mu is the real root of this particular equation. And in this case, mu is approximately equal to 1.8393. You can compare this with the secant method, which is order h to the phi, where phi is the golden ratio, that is the solution to x squared equals x plus 1, and that has a rate of convergence of h to the 1.6180 approximately. And so this technique will converge quicker. There are, however, issues with this method, which is called Muller's method. Specifically, if the function is real valued and the points are real, the roots can still be complex valued. Now, this is actually more useful than the secant method and Newton's method if we are actually finding the roots of a real polynomial that has complex roots, because this will actually move into the complex plane and then converge to a complex valued root. However, this is less useful if we're actually trying to find a root that we know to be real. So we may not want to blindly apply Muller's method if we are trying to find a real valued root of a real valued function. So following this topic, you now understand Muller's method. Like secant method, it interpolates points, however, it is now using quadratic interpolating polynomials and finding the appropriate root thereof. You are aware that there are techniques that can be used to reduce the error, shifting to the origin and using the appropriate formula for calculating the root of a quadratic equation. You understand also that Muller's method may diverge or result in complex roots even if all the values are real. You also know that the secant method is order h to the phi, whereas Muller's method is order h to the mu, which is slightly greater than 1.8, which therefore converges almost as quickly as Newton's method, which is order h squared, at least for an appropriate root. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!